right, good weekend, ladies and gentlemen. This is Mr. Collins.
And Mr. Martin.
We're going to talk to you a little bit about this whole function thing, this reversibility thing, and how that's really going to affect our study of trig. So, I'll go ahead and start with like this right here. What we kind of did is we took everybody's list and we kind of put them together. So what we have here, which you really take note, is the indisputable definition of functions. Like this is the one, no matter what book you go to, what source, they will tell you this is a definition of function. One output for every one input. You give me an x, I should be able to give you a single y to match with it. That's not what we were disputing. What we were disputing is all this other stuff that goes along with it, particularly like some of the things like mechanically do you always need an equation or a graph, and then really this idea of predictability and reversibility. In other words, if I give you an output, can you get an input? So we designed kind of this green sheet to help you think about it, but we know there's some confusion, so that's kind of what this video is about. So without further ado, let's just jump into it.
Okay, so for the bacteria problem, this actually is a true problem. This is actually how bacteria divide and multiply. So in case you ever decide to go lick your desk or something like that, you should be able to calculate how many bacteria you have there. But with this first one, the graph is actually an exponential graph. I know that you haven't had a whole lot of experience with solving exponentials, but I think that's okay for our purpose here. And the question really goes over, we want to know how long it takes for the bacteria count to get to 2048. There are a couple ways you can do this. One, you can make a map. You can go through every hour and see if you can come up with the correct hour. But a more useful way would actually be able to graph the output that you're looking for, in which this case is 2048. So on the y-axis, which represents our outputs, we can just graph 2048. In this case, y equals 2048, which we're just kind of estimating here. It's not 100% precise, but it gets the idea across. And when solving that, I think that we come up with the, I believe is 11 hours for that one. The other part, actually I guess the first part technically, goes over how many bacteria are present after 6 hours. And that's another calculation, one you can quickly solve, which we know you can do that. But that's not what the whole idea here is. We want to be able to look at this graph and determine, well, first off, is it a function? It does appear as a function. It looks like for everything you input, you get one and only one output. And then the other question, is it reversible? Can we reverse that? So for instance, if I have 2048, can I actually come up with the exact time the bacteria count is at 2048? And yeah, we can. So based on that, it looks like, yeah, this is a function. It's one that we can reverse. It also has a graph and it has an equation. It has a pattern too. So I'm not so sure that this one helps us out a lot. But I think that it actually helps us to look at where we're going here and what we need to look at, and that is are the well, let me think about what. No, the thing we're looking at here are the values. Can we reverse everything? What are the rules for reversal? And so keep that in mind as we keep moving here.
Yeah, so let me just make sure I kind of hear you right, Mr. Martin. So the first thing you said is that this is a function. And the way we're kind of confirming that is that we're looking at this kind of input-output thing. Ooh, yellow, bad choice. So if I have like an input of 6, that's going to give me just one output of 64. And there's no ambiguity there, right? Like, so am I reading that right, Mr. Martin? So like, if I give you an x, you can predict a y, no problem.
Yep, looks like that's what we can do in this case.
So along the same lines, then it seems to me that you're saying if I give you a y, you should be able to give me just a single x value. So in that sense, like you can say this one is reversible, or like you can map it backwards. We're not making a map, so I'm not using that terminology, but this is reversible because I give you like an output of 2048. There's a single input of 11. And there's no question that that's the input because the way the graph is shaped, so to speak.
Yeah, absolutely. I mean, if you think about it in terms of practicality, it doesn't make sense for that output of 2048 to occur 2 different times, based not only on the graph, which, yeah, it clearly is going up constantly, but just on common sense. If you think about bacteria, they continue to multiply. They're not going to go back down unless you decide to kill them. So 2048 should really only happen at 11 hours.
So kind of looking at our list, it doesn't really seem like I can really take anything off at this point. Because that one did have an equation, a pattern, a graph. It did have the same number of inputs and outputs, which I don't know if I know what that really means yet. Domain and range must be the same thing. Well, we could probably take that out. because one was time, one was bacteria count. Those aren't both time; they aren't both bacteria. So it seems to me we could have like mismatching domain and ranges in terms of the objects. Predictable input, output, predictable output, input, and reversible all seem to be okay. Let's look at the quadratic one. This is my favorite one. So I'm going to a graph. I'm going to graph this thing. I know this was a mess of a, of a question. That should have been a T. That should have been a 5.5. It happens. No big deal. So we're looking at this quadratic graph. It looks something like this. And then we're kind of asked to evaluate when it's 5.5 feet off the ground, and 5.5 feet happens pretty fast. So something interesting happened when you use the graph to figure this out. If this was 5.5 feet, it seems to me that there were two distinct answers. One was like 0.48, 0.48-ish, I don't know exactly what it was, and the other was like 0.57-ish. So I come to the quick conclusion that I can't answer this. Now, I still claim that this is a function, because if I give you a single x value, like, I don't know, 0.6 or something, I can find just a single time, so it maps one input to one output pretty well. So like if x equals 0.6 seconds, there is like a height, I'm just going to make it up, like 5.2 feet, where 0.6 is the only value where that 5.2 feet is going to occur. No, I'm sorry, 5.2 feet is the only value at 0.6 seconds. But I would claim this one is non-reversible. Because at 5.5 feet, I have two distinct outcomes. I don't know which one is the real answer. What do you say, Mr. Martin?
I don't know. It looks like they both could be the answer to me. They both make sense. I mean, it's going forward in time, so maybe it happens at both times. But which one am I curious about? I don't know.
Yeah. So like here's 5.5 feet. I could have the x value of 0.48. I could have the x value of 0.57. So that's why I'm saying this was non-reversible, because I don't know which path to take. Ambiguity, non-reversibility. So let's go back to our list. Let's go back to this guy. So do you see anything we can take out then?
Well, that's a good question, Mr. Collins. I think that based on that, maybe we're thinking that we could take out the predictable input for a given output, because clearly that second one, other one, I think. Reverse. Yeah, that one, predictable input for a given output. Because that one, clearly we cannot predict our input for an output. I mean, 5.5, it's either one or two, we can't predict that. But the first one we did, so I don't know if I'm comfortable taking it out completely, but it looks like that there might be a question here. I don't know as well.
Yeah, I'm on the same kind of boat. Like it's almost like I got an asterisk. It's like, yeah, it's not always reversible, but it does seem to be at least sometimes reversible. So maybe we need to start shaping our question to which ones we need to take out, to which ones we have to define when it happens and when it doesn't happen. So with that being in mind, we looked at the graphs. Let's start looking at some tables, or some maps, I should say.
Yeah, so this one is the random name generator. I don't know if parents actually use this. I might consider it if I ever have a kid, but who knows. But these two, Jedi and Apple, real names. People have actually named their kids this. So for those of you who don't believe it, look it up. It's true. So this one, apparently this random name generator is broken. It's only giving out Apple and Jedi. So if I put an even number, I believe that one should go to Jedi. Which I don't know if that's a boy or girl's name, but it's probably a guy's name. Who knows? So even number, only going to Jedi. Odd numbers just going to Apple. So it looks like we actually have only two possible names in our range here, or our outputs. So it looks like we can predict. It looks like for each input, for instance, 1, that goes to Apple. We know that for sure. It does not go to Jedi. We know it only goes to Apple. And 2, for instance, goes only to Jedi. Same with 3, going all our odd numbers going to Apple. Even numbers going to Jedi. So it looks like it's a function, because for each input there's one and only one output. But then we start to look at reversibility here. For instance, if I input Jedi, or if I get the output of Jedi, what number did I originally input? It looks like we have different possibilities: 2, 4, 6, 8, or 10. But again, the question that we asked in class, which one? And I don't think we can answer that. So it looks like, based on that very example, it's not reversible. We cannot reverse this one. I'm curious, Mr. Collins is actually the one here doing all the drawing. He didn't draw a graph, Mr. Collins, so I'm kind of curious, why did you not put a graph up there?
Yeah, I don't think we can even put a graph for this one. Like, what in the world would I even graph when these aren't necessarily numbers? Like, the coordinate grid takes numbers well. I'm not saying you couldn't graph it like if you wanted to, but it's certainly not as natural as graphing something like this, where all the numbers are naturally, or all the inputs and outputs are naturally numerical. I guess we could assign a number to output or to Jedi and Apple, like make it Jedi 0 and Apple 1, and then I bet we'd see even more clear as a function. But again, why force it? Like I didn't need a graph to solve this, which indicates that you don't necessarily have to be able to graph it at all. And I think the important thing here too is to kind of consider the maps themselves. Like, Mr. Martin, you mentioned this was non-reversible. I agree. Like, if I have Jedi as an input, look at all these different outputs I could use. So, I mean, that's going to be even says 2, 4, 6, 8, 10. I mean, that's 5 different possible outputs for Jedi. So the reversibility here is impossible. So it seems to me we have a function that's not reversible here. But I bet we can even take some more stuff off our list.
Yeah, I think we said we can't make a graph. That one's definitely hard to graph. Even furthermore, the equation. I mean, how do you make an equation there? I don't know how to make that one. I'm pretty sure that most of you, if you can't make an equation, come let us know, because we'll be happy to hear that. So it looks like 2 more things. We can take off there.
Oh, we could probably take this one off too. There are only 2 outputs that all the inputs went to, so we could probably take this one off as well. So functions can have uneven, how am I trying to say this? They can have inputs and outputs of different numbers. Like, you can repeat the outputs.
Yeah, so for instance, if I have 10 inputs, I'm allowed to have just 2 outputs.
Okay, so we're working this on, and again, the question you should have in kind of your mind is like, what kind of creates this non-reversibility? I mean, so we saw a reversible graph, a non-reversible graph, a non-reversible map. Let's talk about this one in terms of maps. So here's BK, Brian King. He's going to call an exterminator. So I'm going to make this a map. I'm pretty sure I could graph it because it's all numbers. But I'm going to go ahead and map this out because it doesn't seem to be a lot of numbers. Calls. That should be an S. Whatever. Okay, so I'll see. He calls on person 1. He calls 5. 2. He calls 4. 3. He calls 1. 4. He calls 10. 5. He calls no one because he was taking a break. 6. He calls 7. And then on day 7, did I mess up? Wait. Oh yeah, 7 he called 3. Okay, I kind of lost the reading there. So on the map, I made it easy. I'm just going to map straight across here. And some of you guys caught on a table is nothing more than that's a really well-ordered map. So I guess you can say I made a table here as well. So his wife noticed a bill and said he called 10 people. On what day does this happen? Well, first of all, let's establish functionality. 1x only traveling to 1y. We don't see a doubling up effect. We don't have any ambiguity on the output. So this is definitely a function. 1x for 1y is definitely preserved. Let's talk about reversibility. Well, can I even answer this question? He called 10 people. Well, here's 10 for the output. Could I predict the input? Well, yeah, obviously, right. Like, it's tracing back to a 4. I don't have any other things that call 10. This one's going to be a reversible function. Now, we're using the word reversible. We'll probably give that a better we'll probably give that a better name eventually. So just kind of keep that in mind. We're calling it reversible for a reason, just to kind of give you a sense of what's going on. So, Mr. Martin, I think at this point what we really need to do is kind of decide like what makes things reversible or not. Okay, so do you want to take the graphs or want to take the maps?
I'll take the graphs.
Okay, well, let's take a look at the graphs.
Okay, so if we're trying to reverse something, one useful thing we can do is look at the graphs. For some of these, we don't have graphs. So it's going to be kind of difficult to talk about graphs, the ones we can't have graphs. But, so if we're looking at a graph and we want to reverse something, there's a couple things that we need to note. Yes, graphs. There we go. So this one, if you look at it, I can look at that graph real quickly and say, well, it looks like for every x value I pick, or input value I pick, there's only going to be one place that I can find a y value. It only occurs at one point. For instance, 664. My input of 6, I get 64. Based on the graph, that's the only place it occurs. Same with 11. I know that my input's 11. The output's 2048. That's the only place it occurs. But also, when we're looking at reversibility, the same idea. If I know that my output's 2048, there's only one x, and that happens at x equals 11. Same thing with 64. My output's 64. I know that only occurs at x equals 6. So that's a case. This is a case, an exponential case of when it does happen, when it is reversible. Let's look at one that's not reversible. This one's a quadratic. My output 5.5. It happens at two places, and I can tell that quickly from the graph. There's actually a line here representing 5.5 feet. That line goes across. I see that intersects at two different x points, x values, 0.48 and 0.57, if I can talk. So those two values, my output this one is not reversible because my output happens to go to two different x values. So using the graph, if we pick our output, just look at the graph. See if that output, in this case 5.5, crosses over and touches two points where there'd be an x value. So that's one way to use graphs to see if they're reversible.
Yeah, it's almost like, Mr. Martin, it's almost like you're kind of mentioning, we know about the vertical line test for functions. It's almost like you're mentioning like a horizontal line test, if I'm reading that right. So like, if I look at this horizontal line, there's only one intersection, you said, and that kind of indicates reversibility because you don't have another choice where that y value could occur. And here you're saying, well, look, horizontal, boom, hits it twice. That is going to be non-reversible because you're going to have a choice on those x values because it does produce two. I think I'm seeing the same phenomenon here. So I have these maps. I'm looking at 10 numbers on this side, looking at 2 numbers on this side, non-reversible. That would kind of be like drawing that horizontal line and hitting 1, 3, 5, 7, and 9 all at the same time. And here I'm just kind of thinking about the graph would look like. These would all have their own individual horizontal line. So I'm kind of taking what you're doing on your graphs and I'm transferring it to maps, and I'm thinking, dang, if they have even numbers even meaning the same numbers of inputs as outputs, it seems to me that it's going to be reversible like it is here. Say they have 7 numbers here, 7 numbers here, and then over here we have 10 numbers, you have 2 numbers. That's non-reversible. It seems like that's kind of how it's playing out, like with your graphs. Two values, one value of y, 2 values of x. That's an uneven mapping for domain and range. Yeah, I mean, kind of like kind of non-reversibility. So it seems to me the last thing you have to do is kind of lay these down into a rule.